Okay, welcome everyone to today's discussion session. We're going to follow the same format as in the previous days. We have three members of the panel, so I'm going to chair the discussion. I'm going to ask a few questions. I've prepared three, but let's see where we get. I'll start with the first question to the panel. Each member of the panel gets a few minutes to give us their perspective on that question, and after they have all answered or discussed, then we open up the discussion to everyone, and hopefully we find some interesting topics. Good. So our panel members today are Dvali from Munich, MPI and LMU, Paolo Benincasa from NBI and IFT in Madrid and NBI in Copenhagen, and Austin Joyce, currently at UVA in Amsterdam, but in the near future in Chicago, I guess. So thank you very much for accepting to be in the panel. So I'm just going to say a couple of words, and then I'll start with the discussion. I didn't prepare slides, but so I wanted to frame the discussion around perturbative quantum field theory around curved space-time. It's a topic that we are interested in because it seems to be the language needed to answer some questions in cosmology. In particular, that's the tool that we have to actually make precise calculations, both for models of the early universe, inflation, but also late universe, dark energy. And because we hope that that's a path to better understanding the properties of quantum gravity, perhaps. I would say that in using perturbative quantum field theory for cosmology, perhaps there are various ways to think about it, but I can think of a couple of phase transition in the past 30 or 40 years, historical phase transition. One phase transition took place about 20 years ago, and until the early 2000s, people were mostly interested in two-point functions, mostly free theories, computing power spectra. And that really around 2000, 2002, with Maldasena's seminal paper, and the interest also from the point of view of observations in measuring non-Gaussianity, really a new field exploded in which we were starting to actually measuring interacting quantum field theories and computing three-point functions and four-point functions. And perhaps the interest started slowing down and decreasing a little bit after the negative detection of Planck, even though there was no good reason why Planck was supposed to detect anything. And perhaps another, perhaps smaller phase transition has taken place recently, in which there is renewed interest in understanding more generally perturbative quantum field theory in curved space-time. And especially when I say curved space-time, I really have in mind FLRW space-time, mostly accelerated and mostly quasi-de Sitter space-time. But I think a lot of the tools are going to be valid more generally. So why is there this renewed interest in perturbative quantum field theory in FLRW? Well, on the one hand, if we really think this is the theory or the correct description of the very early universe, it's a bit embarrassing that we actually are able to, or in the literature we have computed only the very first few and simplest correlation function. I mean, state of the art, we are talking about 3-level 4-point function with massive exchange, or until a couple of years ago, that was the state of the art. Or maybe one loop 2-point function, so power spectrum, but not very much. I mean, comparatively to what we do in flat space for particle physics, that's embarrassingly little technical ability. And so there were various developments in the past few years in which we developed new tools to make faster calculations using perturbative methods. And therefore, we were able to access a wider range of observables, more complicated correlators with spinning external fields, spinning exchange fields, massive fields. And part of the motivations was to understand the theory better, but another part of the motivation was that we were betting on finding some new structures when we collect enough data, enough perturbative results for correlators. We were betting on the fact that we could recognize certain simple properties of the answers that were not obvious a priori before we did the calculations. And by peeking at the result, we could find better ways to do those calculations. Some of this progress actually had happened in amplitudes, where it took a long time for people to do complicated calculation and realize that the result was very simple. And here is the same. It's just that we don't have a large amount of theoretical data available to us that we can survey to find simple results. And so the idea is that with better technology for computing comes also better understanding, and that's the direction in which we want to try to push this. For example, it was a bit embarrassing that although in every quantum field theory book that you would pick up, there would be a chapter dedicated to consequences of unitarities for quantum field theory, and you would have your optical theorem, your cutting rules, and until 2 years ago, no one would know what the consequences were for correlators. Similarly for locality, also locality until a few years ago, it was relatively unclear how that such a fundamental notion was encoded in the correlators that we observe in the sky. We understood things a little bit better at the level of symmetries, but even there is much that we should do, especially because of the crucial role that gravity plays and the associated diffeomorphisms and large diffeomorphisms. So within this framework, I wanted to propose 3 questions for discussion. And the first question was, now that we have been making progress in perturbative calculations in FLRW, what are the deepest questions that we can try to answer using these advances, using perturbative calculations? Clearly, we can compute 3-point functions and 4-point functions, but is there some qualitative understanding that we can hope to reach? And if yes, what do we hope to understand? And how do we hope to understand using perturbative calculations? So I want to start asking these questions. I think I should go in alphabetical order, perhaps. Who's first in alphabetical order? Let's go by family name: Joyce, Dvali, Benincasa. Paolo, so why don't you start?
Can you hear me? Okay, perfect. First of all, thanks a lot for inviting me to be a member of this panel. And so I think I will start by why. I've been studying the properties of scattering amplitudes for a long time, so I'm not really. I was not really an expert on thinking on what's happening in curved space. But what dragged me into this field was actually the one that for me is a really important question, which is what the rules, the fundamental rules governing physical processes in an expanding universe. Which means that, for example, we now have our preferred observable, which they will define just in some approximation when we're talking about an expanding universe. So if somebody hands them to us, what should we check what should we check to see if this, no matter how it has been computed, are right or wrong? So in the last years, there have been some progresses in this direction, like the cosmological optical theorem that Enrico and collaborators introduced. There has been, we heard from Daniel that we learn about the singularity structure, we know more about singularity structures. We know that there are some special singularities which are not supposed to be there. We also have started to have some links, perhaps, to causality with, we found some Steinman-like relations. So, but the question is that it is still, is all this enough? All this, at least perturbatively, that is what we are interested in this context. Can they fix at least the tree level once for all? And for some comments that Daniel was making in his talk, it seems that it might not be the case yet, or at least we have not learned how to deal with these new tools that we learn. And in this sense, and it's important to start to address perturbatively, because also, for example, in scattering amplitudes, we know a lot perturbatively, even if not at all loop orders. We don't know these rules at all loop orders. And even in the context of scattering amplitudes, we don't have a complete full-fledged understandings of fundamental concepts like causality, unitarity, etc. So it's good to have to start to address these questions from starting from perturbation theory. And another thing that is important that all to keep in mind, that all the has also Daniel emphasized, is that all this progress has been made in a graph-by-graph analysis, which is fine when we are analyzing scalar states, but becomes not fine anymore when we want to deal with the spinning states. And also we saw this in amplitudes, that a lot of magic symmetries, a lot of structures showed up once we learn how to deal with the full object at once, or in a better representation which gets rid of gauge redundancies. And this is still a very open question, because also the computation that Daniel showed are also, even for spinning states, are graph by graph. On the similar line, one fundamental concept that we have in flat space, and it's related to locality, is the notion of cluster decomposition. Now, if you think carefully, if we consider massless states in an expanded universe, they grow, the two-point function grow logarithmically, which means that when you separate the two states, it blows up. So you don't really have cluster decomposition for massless states. How do we understand this? There was an approach by Aninos and Denef of some years ago, but still we don't really understand how this can be encoded in the observables in a sharp way. And this is another open question that I think is very important to address, and is related to the general question of what are the rules that can fix the observables. There is also the general issue of perturbative stability of the sitter. There are two lines of papers, one claiming that there is no such an issue, other claiming that actually is completely unstable. I think that learning how to do calculation, even in this case at loops, might be will be useful. Might start to shed a little bit light on this issue. Which of the two strands are? Maybe we can put a final point on this this general question. And one last point, which is more connected with a very first principle understanding of the physics in an expanded universe, is really all the approach of this bootstrap approach relies on the idea that we should be able to reconstruct this cosmological correlators or wave function of the universe from boundary data, because at the end of the day, they are objects which lives on the space-like boundary of this expanding universe, and they have the time evolution integrated out. One thing is learning how to compute in this way, but also I think we should learn what if this correlation function has thought directly living on this space-like boundary, might define a theory on its own that lives directly on the boundary without thinking anymore about this time of evolution. And this is is related to the general idea of having an understanding of holography. Because if we can really do that, if we really have a full-fledged theory on the boundary, which we know, or we conjecture, we have the right to conjecture, which is which is equivalent to our cosmological theory, Then we even have information about what's the Hilbert space and all the quantum mechanical information about the system. So it will be a full-fledged definition of a quantum gravity system in the sitter, or in more generally in an expanding universe. And I think this is an open question. There are several approaches to this, and one can start to think about try to make up what is the CFT, or thinking about I can forget about anything. I want just to try to make up, to try to create a mathematical question whose answer are cosmological correlators and or the wave function of the universe, and all the other properties are emerging, and this will create my new theory. These are different ideas that already are on the market, but I think more generally these are the problems that is a big problem which may address some we can learn from perturbative methods, something which can go beyond actual perturbation theory. And then this is I think something that we should value. And,
okay.
Yeah, I will stop here.
Yes, thank you very much for your perspective. The next one is Gia. So Gia, floor is yours.
Hi, can you hear me?
Yeah, loud and clear.
Hi, yeah, thanks for the invitation. Can I share the screen actually? I scribbled a couple of...
Yeah, I think you guys are all co-hosts, so you should be able to do it.
So you see the screen, right? So you see the full screen?
Now it's dark. But
it's dark.
At least on my, yeah, now it's dark.
Now it's a black hole.
Okay, stop sharing then. No. Okay, share now. What about now?
Yeah, it's good.
Okay. Yeah. Thanks. Yeah. Thanks very much. First of all, for the invitation. Yeah. Unfortunately, I could not speak on Thursday because of teaching. So therefore, I scribbled a couple of things just to communicate some background view, slightly complementary. So basically, the point is about S-metrics. And so S-metrics in string theory or in quantum gravity in general, the way we know it, is not just a calculation tool, but it's a formulation of the theory. And now, when we talk about card backgrounds like the sitter, I will mostly be concerned with the sitter. Intuitively, it looks like after all, we cannot define already at the classical level. We understand that there is a problem because we cannot define globally time. S-matrix requires globally defined time, but at least we think that we can do some effective S-matrix description. After all, we do S-matrix computations at LHC, and they look fine. And okay, so at short distances, we could do something. Now, the thing is that, however, that's not true actually for gravity. And the reason is that the S-matrix on top of globally defined time also needs a vacuum. And that's super important. So vacuum should not be able to recoil. Because if vacuum it recoils, okay, here you can see this is sort of pictorial in the sitter. You have a scattering process, in states, out states. And now if the vacuum recoils, then you cannot formulate an S-matrix, because every time your set of in and out states will depend on what happened during the scattering process. And this is a fundamental problem. It looks like a small detail, but it's not. And now we can see this from the double scaling argument, the following double scaling argument, that if you want to make a rigid limit of the vacuum, in which vacuum doesn't recoil, the only possibility is to take Newton's constant to 0, and you have to take correspondingly cosmological constant lambda, the vacuum energy, to infinity, and keep the curvature radius fixed, finite. So this, of course, also is equivalent of taking Planck scale to infinity. And now if you do this in this limit, or in string theory, this is equivalent of taking string coupling to infinity, closed string interactions go to 0. And so therefore, gravitational coupling or string coupling. So here Q is a momentum transfer. So the graviton coupling depends on momentum transfers. And so they both go to 0. And by the way, it's important to notice that this is not true for other interactions. So for example, if you have an interaction which is asymptotically free, like QCD, or some other interaction, you can keep that effective S matrix description fine, even in this limit, because you can keep a coupling constant of other fields finite while you take this limit. So it's really intrinsically, this shows that there is a fundamental connection between gravitational S matrix and the curvature, and the curvature of the space-time. So therefore, S matrix tells you that that de Sitter cannot be a vacuum. And so therefore, the only option left in S matrix formulation is that the de Sitter therefore has to be a state constructed on top of a valid S matrix vacuum, such as Minkowski. And this introduces a new concept, which we call corpuscular completion or corpuscular resolution. And this is very different from ultraviolet completion of the theory. Actually, it's not sensitive to ultraviolet completion of the theory, because you are resolving your state quantum mechanically in a quantum state at arbitrary large distances. Okay, so this is similar to if you have for example, a laser pulse of very long wavelength. You can resolve it corpuscularly as a coherent state of photons. And so here the same is imposed upon us by S matrix for de Sitter. And now so this means that de Sitter is viewed as a state, and now certain model independent aspects emerge immediately as soon as you do that. You discover that de Sitter is a saturated state. Saturated state means that the occupation number is given by the inverse of the strength of the coupling of the constituents. So it saturates this in this sense, and it also saturates the entropy bound because of this, and it's very important. By the way, immediately you can see that there is emergent theory of gapless modes, which actually account for the entropy. That theory is not conformal. That becomes approximately conformal only in this rigid limit, in which you decouple gravity. So again, you see why it's not so easy to do de Sitter and conformal field theory. Connection or correspondence, because you have to decouple gravity if you want to do something with this theory. But anyway, this is not the main topic I'm interested in. I don't know what happened here. Yeah. Now, of course, this gives a different view on de Sitter. So now, what you have to do, what before you thought was a curved space, you treat curved space as a background and do some processes on top of curved space. Here now, the curved space itself participates as an actor in the performance, which is a fully quantum performance staged on Minkowski vacuum. So now the curved space. Now, of course, you can, by construction at short time scales, you can see that you reproduce precisely the treatment of theory on curved background. But this theory therefore gives you this treatment gives you more, which is hidden in the semi-classical treatment. In particular, it opens up corpuscular effects, and there are several consequences. And one consequence is universal consequence is so-called quantum breaking. Simply, there are no systems in nature no saturated systems in nature that do not quantum break after this time scale. Now, quantum breaking is not any stability, okay? So this is not what I'm talking about. It's a departure from the classical description, a fully fledged departure from semi-classical mean field description. And this only happens fully for saturated states. Normal states experience, of course, quantum corrections and stuff, but normally macroscopic objects, they are reasonably well described classically. But the saturated states, they are not. They sooner or later, they quantum break. And for de Sitter, that's a disaster. And this tells you that, so there is now the chain closes, S matrix circle closes. S matrix imposes upon us that de Sitter must be an excited state on Minkowski vacuum. And that immediately tells us that de Sitter should quantum break. And therefore, there is an absolute bound that any de Sitter-like state in string theory or in S matrix quantum gravity in general should exit, should find grateful exit after the time less than the quantum break time. Now notice that this quantum break time is a power law time. It's much shorter than all these exponential decay times of metastable vacuum and so on. So in some sense, this quantum breaking time makes all these tunneling processes irrelevant, because de Sitter quantum breaks way before it has any chance to tunnel. So it has to find graceful exit, not via tunneling, but by some more fast evolution, like classical evolution. And of course, this excludes any metastability or stability of de Sitter, and which is, I think it's great, because this is the way string theory tells us that actually what we thought was a problem was never a problem. So there is a cosmological constant was never a point of naturalness, it turns out, in this approach, of course. It's a problem of consistency. So it's like anomaly cancellation. So there is this consistency issue, and that's it. And basically, this is there are plenty of course, consequences also observationally, because these corpuscular effects they get imprinted in the observables that would be extremely interesting to study. But the direct relevance to your question, what you asked, is that this complementary view on how to deal with Carr spacetimes interactions in Carr spacetimes. In this view, we can think we can treat Carr spacetimes themselves as states on top of S matrix Minkowski vacuum and study from that perspective. And so this is of course this complementary, as I said, for timescales shorter than quantum breaking time, treating Kerr space as a background is perfectly legitimate. There's no problem with it.
Okay. Okay. Yeah, that's great. I mean, thanks a lot, Guy. I think we will open it for discussion, and hopefully we can have.
Yeah, I'm done. Yes,
thank you. That you have a perpendicular point of view on the problem. But I wanted to give the chance also to Austin to address this, and then we will open up, and then we can have a discussion. So please, Austin, floor is yours.
Okay, cool, thanks. Yeah, I'll try to go relatively fast, but let me start by saying thanks to Enrico and David and the other organizers for organizing this nice meeting, and thanks for giving me the opportunity to take part of this in this discussion. Yeah, so let me just start by strongly agreeing that studying quantum field theory in cosmological spacetimes is sort of interesting in its own right, and it's something we should do, and there's sort of many interesting things to understand. Along the lines of what Enrico and Paolo were saying. But of course, every now and then we want to sort of take stock of and try to understand like what new insights we've gained, how that will let us solve other physical problems. And so it's kind of interesting to think a little bit about where we think that these techniques that people have been developing may be useful for cosmological questions. And so to me, sort of the most beautiful thing about cosmology or inflation is that it links the UV and the IR. And so I'm going to try to like group questions that I think are interesting to answer that may also, you know, there's some line of attack into sort of boxes depending upon UV and IR. And so I'll start with the IR, and it's kind of related to what Guido was just saying. Like, I think one of the more interesting questions we could hope to at least start to try to address perturbatively is to understand something about these claims that de Sitter space is even perturbatively unstable, or to understand something about slow roll eternal inflation, which sort of actually seems kind of like a breakdown of perturbation theory, but you might hope that by starting to resum things, you could get some handle on what exactly is going wrong and learn something new at very long distances. And one reason that you might think that these sort of modern techniques would be useful in these arenas is that, like I just said, oftentimes these are questions of resummation or the breakdown of perturbation theory, and having some more efficient way to compute higher order or higher multiplicity objects can be quite useful. And I should also mention that there's been a lot of recent interest in understanding sort of the IR structure of de Sitter space and field theories in de Sitter space. And so I'm optimistic that there can be some connection between sort of these more formal bootstrap type approaches and the understanding about IR physics in de Sitter. And very much related to this, I think sort of a not very like flashy or exciting topic, but something that's like super important to understand is understanding what's going on with loops in de Sitter space. So of course, there's been a lot of work done in the cosmology literature, but I think no one would really dispute that our understanding of loops is still very primitive, especially compared to that in flat space. And it's really an important question for a couple of reasons. One is that we rely very heavily on cosmological perturbation theory, right? We compute the temperature spectrum of the CMB using cosmological perturbation theory at tree level. But we should understand the theory well enough to compute the one loop correction to that if we so wanted, even though everyone believes that it will be very small and will not be of consequence. It's like important to be able to do this calculation just so that we know what we're doing. And then another reason, something I think we'll talk a little bit about later, is that a very powerful connection between IR and UV comes through dispersion relations and positivity bounds and things like this. And in order to derive such dispersion relations, we really need a strong analytic handle on the structure of like singularities and cuts of cosmological objects. And the simplest way to do that, or at least to start to get a handle on that, is to understand at loop level. And so I think we really sort of need to try to march forward on that front. So that's sort of IR issues, and I'd be very interested to hear what people have to say, both about this and just in general about the question of like, what is the most interesting thing we could hope to do perturbatively? So sort of on the UV end, like I said, a very powerful feature of cosmology is that by measuring large-scale structure or non-Gaussianities in the CMB, we can hope to learn something about UV physics or physics at the smallest scales. And one of the sharpest ways to do this is through dispersion relations. And so I think a very useful and interesting thing to do is to try to develop this technology of analyticity and positivity in cosmological backgrounds. Related to this sort of UV question is really the question of UV completion. So Daniel also already mentioned this, maybe he wants to say more at some point, or I'm sure Guy would, that there's like a totally concrete question about UV completion in de Sitter space, which is to search for the de Sitter or cosmological analog of the Veneziano amplitude in flat space. You could call it the Veneziano correlator. And this object has to have like definite properties. In particular, it shouldn't have this total energy singularity that Daniel was talking about. And it should have a characteristic sort of oscillatory features when you approach a particular kinematic configuration. And so there's like a totally well-defined mathematical question about whether or not this object exists. And you can think of it as having a similar status to the Veneziano amplitude, that it would give you some rough handle on what string theory could mean in de Sitter space. And so I think finding such an object would obviously be extremely exciting. So Paolo already talked about this, but of course, one of the motivations for doing all this kind of reformulation of perturbation theory is to understand something about the emergence of time or cosmological holography, which we should talk more about, but I'll just leave it there. And then kind of something a little bit out there that doesn't really fit into these UV IR boxes that I was talking about, but maybe it would be interesting to discuss, is that sort of a motivation for thinking about perturbation theory and cosmology from this more on-shell or boundary perspective, for me at least, is that many of the canonical problems that we associate with inflation are uncomfortable things like the eta problem or the measure problem or low entropy initial conditions are really tied to our sort of UV-like completion description, where we think of inflation as being driven by a single weakly coupled scalar field rolling in a potential. And so I'm kind of optimistic or hopeful that getting away from this picture of like a scalar field and a potential may give us some new insights into these questions, maybe give us some way of understanding or dealing with them. So I'd be very interested to hear if anyone has anything to say about that. But okay, I'll stop there and maybe we can discuss a bit.
Great, thank you very much, Austin, and Guy and Paolo for your views. And yeah, it would be nice to open up the discussion and hear other people, especially if you have questions. So I can see, please, as Kurt just did, find your raise hand function on the bottom and do it. If you cannot find it, you can also write to me on the chat, and I keep track of who asked me. So Kurt, please go ahead.
Hi, so I had a question for Gia. So you mentioned the necessity of having a globally defined time for the S matrix, but don't we also need asymptotics that are flat? Like so anti-de Sitter space, does that not have a corpuscular description as well?
Yeah, actually, that's a very good question. So I was focusing here on Minkowski because of the just practical reasons, because I know how to work out the sitter as a coherent state on top of Minkowski. But if any other S matrix vacuum, if you can define S matrix properly, could serve the same purpose. Now, I don't know how easy it is to do the same construction that we did for the sitter if we start from ADS as an S matrix vacuum, because in ADS, as you know, the way we effectively define S matrix is, in a sense, is through ADS CFT correspondence. So in ADS, somehow it's safer to go through ADS CFT correspondence. But the answer is yes. Yeah. Anytime you have an S matrix vacuum, you can do this. You can develop this approach. Now, by the way, this also resonates with what Austin and also Paolo were saying. So, for instance, this UV-IR story, right? Let's take this Veneziano amplitude question, right? Which is a very interesting question. Now, if I'm treating the sitter as a vacuum, of course, I'm facing this question, how to define this amplitude in this new vacuum. But if I'm thinking of the sitter as an excited state on top of Minkowski vacuum, then defining, conceptually, defining Veneziano amplitude in the presence of the sitter is not that conceptually different from defining Veneziano amplitude in the presence of gravitational wave or of sufficiently high amplitude. Of course, there are technical differences, obviously. I mean, I'm not trying to trivialize the story, but what is important is that Veneziano amplitude in the presence of high occupation number gravitational wave, we know what it is on Minkowski background. That's a S matrix process in which many quanta participate. So it's not 2-to-2 scattering process, but it's actually large n into large n scattering process, because we have to view high occupation number state of gravitational wave as a participant. So it's the same story with the sitter. In this approach, so it effectively will be Veneziano amplitude imposed on multi-particle scatterings. And so I think that this is the pathway. So in other words, understanding there is a correspondence between understanding scattering amplitudes on curved spacetimes and between scattering amplitudes, high occupation number scattering amplitudes, large n into large n on the flat space. We have checked this. At least two groups have checked this for 2-to-n scattering on a flat space in case of black hole formation. And actually, it turns out that this stringy scattering amplitude, my collaborators at I and another group with Veneziano, Bianchi, and Adasi, and as well, Dieter Lust, Cesar Gomez, Stieberger, and others. So we saw that this actually, precisely at the critical point, it reproduces precisely the entropy suppression for each microstate that you expect. A fully fledged stringy computation of 2-to-n. And I think so that's the pathway to go. So it's a multi-particle amplitudes are the correspondence to amplitudes on curved space-time backgrounds. It's just one aspect of.
But maybe one concrete question that we can ask is that if we were to find, so I mean, clearly there is a difference between an amplitude and the correlator. So I think what Austin had in mind was actually computing a correlator. The main various differences. One is that
of course,
would not have to be conserved, for example. So it's kind of the object that they're looking at is different. So if one were to find correlators that have that are consistent, that they obey all the rules of unitarity and locality, and that on their singularities they show intermediate particles of infinitely high spin in a way that is all consistent. Gia, would you believe, or would you find that evidence that there is a meaning to that string theory admits that the Sitter solution, and that would be a stringy correlator, or you would still?
No, yeah, absolutely. Again, I want to make it very clear in this approach that I'm trying to develop and my collaborators. So in this approach, by no means I'm saying that string theory cannot have de Sitter-like states. Obviously, that would be an enormous stretch. What I'm saying is that it cannot have metastable de Sitter or de Sitter that lives longer than quantum break time. This is clearly what we see from these computations, and I simply don't see any logical loophole what could save that. So therefore, I mean, this time scale of quantum break time of de Sitter is a pretty long time scale. It's not exponentially long, but it's a sufficiently long time scale for allowing to do reliably what you are doing in the Sitter space while treating it as a background, as a reliable vacuum. So difference only comes after that time scale. So therefore, I think all the computations, I mean, look, as usual, I mean, miracles do not happen in physics. I mean, we never completely abolish, when we complete theory by some other idea, we never abolish what was done before. Obviously, computations at short time scales must be 100% valid. Yeah, and the way I see that, sort of not a proof, but the indication of that is that I see that multi-string amplitudes on flat background intuitively, I mean, qualitatively, they reproduce what you would expect happening with amplitudes on the curved background. So at least you see that there is this connection. So one computation and the other computation, they agree in the limit of large n, in the limit when quantum breaking time is taken to be large. So therefore, yeah, I mean, yeah, that would be my expectation.
Would be nice if there was an explicit calculation, no matter how hard, difficult, or long, that one could do within the framework that we understand well, which is perturbative QFT around quasi-de Sitter, that would detect the emergence of a problem. Is there such a calculation? And could you say you should compute this, and then if you find this, then it means the Sitter was an inconsistent solution after some time?
Right. So for finite and Planck, so yeah, indeed. So for example, one computation that I would say is very indicative is that finite and Planck computing the scattering of graviton scattering with the center of mass energy equal to the Planck scale times r square. So if the center of mass energy goes like Planck scale times r square, so that is no way, the corpuscular picture indicates that there is no way to account that while staying in the approximation of a rigid vacuum. You have to include the contribution from the constituent gravitons that make up the Sitter. So for example, that would be a clear-cut test of this, yeah.
And so the object that we should compute, is it a correlator or an amplitude?
I don't think it matters. Anything that deals with that type of energy. So anything that deals either correlator or a scattering at the center of mass energy that probes energy scale of n Planck squared times r. So that anything of that sort should become sensitive to the corpuscular structure of the Sitter.
And r is 1 over Hubble, right?
R is 1 over Hubble, exactly. That's right. So in other words, as usual, it's like there are two ways in which we can understand corpuscular structure, right? I mean, let me give a sort of a toy example. I mean, take a table and assume that we are doing some tabletop experiment, some scattering experiment on top of the table. Now we can think of table as a vacuum, but of course, table is not a vacuum. It has corpuscular structure, and the table recoils. And now we can ask this question: what should we compute in order to be obvious that table is not a vacuum and it recoils? And there are two things: we compute either very high energy processes, or very heavy processes in which many particles contribute. Obviously, if we collide on top of the table, huge number of particles with the occupation number comparable to the occupation number in the table, obviously this correlator computed in this way will not reproduce the true one. And so therefore there are two ways to see. Either we look for very small effects, cumulative effects, but wait a very long time, and this is what is happening in quantum breaking case. So we wait very long. There are small effects, but they accumulate. Or we compute large effects. So these two are the ones that indicate. Basically, what I'm trying to say is that de Sitter physics is large N physics. So it's similar to large N story. And in large N story, either we have 1/n corrections, and either we have to accumulate them, or we have to do some very large number of flavor scattering.
Okay.
And then
thanks. I don't see anyone else raising their hands on this topic. Hi, Maria. Yeah, please go ahead. And feel free to raise your hand when I say it. It means there is a button on the middle, but please go ahead.
My button is gone because nobody of you has updated. I updated to the new version. I don't know what the rest of you are doing. Right, I have many questions, but very quick ones, I hope, or one maybe, for Austin. Austin?
Yeah.
Hello.
Hey.
Just because you mentioned loops, I want to ask, what is the difficulty with computing the loops?
That's a good question. Yeah, I
why
think
we're not doing it?
Yeah, I think the main technical problem is, roughly speaking, that you can't use dim reg. That loops are always of the form like d k over k to the d, and so dim reg. These are just integrals that diverge in all dimensions. So that's like a technical problem that I think has warned a lot of people off of this. But that's not to say it's an insurmountable problem.
Okay, and you said they're not important.
Let me just comment. I think there was a paper by Dan Green and Tim Cohen recently that had made some progress on the.
Yeah, they have a nice way of dealing with this. So yeah.
I would like to know that paper. I would be very interested. And you also mentioned that the results will not be important. I mean, do you have any idea when they might be important? Could they be important? Is there some way?
Sorry, could you say it again? I'm very sorry.
You said that the results from loops, we expect them to not be important.
Yes.
But is there some kind of phenomenological reason why they could be important?
Well, I know in the context of this sort of cosmological collider physics paradigm, if you want to use sort of CMB or large-scale structure observations to understand or infer the presence of fermions, the leading order interactions come through fermion loops. And so if you want to really do these calculations completely responsibly, you have to grapple with computing fermion loops. Aside from that, nothing immediately comes to mind, but luckily there's like 80 other people here, so maybe someone else has an idea.
Well, I mean, I wouldn't say that they're necessarily small. I mean, all of these theories have strong coupling cutoffs that are not too far away. So if you allow yourself, instead of just playing with pure gravity, in which you have the coupling constant being Planck, playing with theories that have more coupling constants, and you crank up the coupling constant, at some point you will find larger effects.
Yeah, but this is always a dangerous game, right? That you don't want them to be so important that you should have considered two loop stuff, right? 10%, 5%. Yeah.
Tell me what your sensitivity of Planck is, and then I give you the coupling constant that does that.
So one example would be a large flavor expansion. I don't know if somebody said this already. In fact, there, just at the level of the matter theory, you can have one loop dominance at large flavor, just like in large N QED. And in fact, we used this recently to produce this log analog of DBI, where it's a log branch cut instead of a square root branch cut, and that was controlled because the one loop that generated that log actually dominates. I don't think this addresses the main point that Austin was bringing up, but it is a situation where one loop matters and dominates consistently over both tree and higher loops.
I think also in a mundane example like the EFT of inflation, if you saturated the experimental bounds from, let's say, 10 years ago, I think the contribution from the one loop to the power spectrum was pretty much within the sensitivity. The problem was that correction.
Really? Because I thought loops are supposed to be down by like h over m Planck all squared, which should be pretty small.
No, I don't think so. I mean, there is CS, right? So are you talking about pure gravity, or are we talking about effective field theories that have self interactions?
Ah, okay. You want some CSs? Yeah, yeah.
I mean, yeah, if it's only pure gravity, then all of this is very small. But now we know we can play around.
Oh, but doesn't CS have to be like 10 to the -4 or something to make up for, or even smaller to make up for this h over m Planck suppression?
No, I think the power is appropriate than 10 to the -2 or so, which is maybe a factor 2 or 5 away from current bounds. I mean, now that would be excluded. The problem there was, well, in the original calculation, people thought that the result was a correction which goes like log k.
Yeah.
That's fantastic. But then there was this set of papers by Saldariaga and Senatore claiming that they did the renormalization incorrectly, and the log k is actually a log h, so that's just a renormalization of the amplitude, which unfortunately we don't know. But nevertheless, the coefficient in front was not small, was of order 1%, 0.5%. The problem is that it was just an overall normalization, so we couldn't see it. But I'm not sure. I mean, it's just the trivial fact that if you crank up the coupling, this is going to be large, and we can find theories in which we crank up the coupling.
That's great. It sounds like you're agreeing with me. We should calculate these loops. That sounds good to me.
I mean, actually, one small addition. Actually, even in gravity, the effect of loops and the effect of gravitation correlators can be extremely enhanced by number of species, and the number of species phenomenologically allowed is 10 to the 32. Actually, that's even nice because that would solve the hierarchy problem. With 10 to the 32 species, the cutoff goes down to around TeV. And so, for example, in general, there is plenty of room for large number of species, and they can tremendously enhance gravitational correlators. I mean, we were pointing this out in different contexts, and so species can have very interesting enhancement effect of quantum gravity effects, actually, and so they should not be dismissed. Yeah. So.
Actually, can I ask about this, Gia?
Yeah, sure.
Do these species, do these renormalize the Planck mass then? Do you have to include that they?
So I mean, yeah, this is actually a very important difference to clarify. The point is the following. Of course, there is a renormalization of the Planck mass. But what I'm saying is that, and sometimes there is this confusion. People think that the only effect that species have is through the renormalization of the Planck mass. But actually they don't, because let's renormalize Planck mass once and forever, okay, for a given scale. Then on top of that, now you have given Planck mass and you have certain number of species. And we can ask this question, given the value of the Planck mass that we're measuring through Newton's constant, how many species we can have in the theory, okay? And up until what scale, then the gravitational cutoff will come down. And there is actually a model-independent, fully non-perturbative argument. So there are several arguments, but the one I like most is the black hole argument. The point is that you can immediately see that why number of species lowers the gravitational cutoff, because black hole evaporation is thermal in species. And so you could see that once you exceed this critical number, a black hole would simply evaporate faster than its size, and this is impossible in semi-classical physics. And so there is this absolute bound, fully non-perturbative on species scale. And then if you look at them, you can see that species contribute very profoundly. Again, for instance, in multi-particle amplitudes. For example, 2 gravitons into anything, you can see that multi-particle amplitude in which 2 gravitons go into n species saturates the unitarity bound precisely at that cutoff scale, and so this other stuff. So species are actually an extremely interesting object for really enhancing gravitational effects. So it would be very interesting to compute all possible correlators and loops, actually. Yeah.
You can see that Cliff has raised his hand. Cliff?
Hi, yeah, can you hear me? Yeah. So I have a question for Austin. So, you know, because there's one of the things that's coming out in this conversation is that there's two separate issues about the breakdown of perturbation theory. One could be that couplings are not small, but another one is that no matter how small your coupling is, at late times you get screwed in places like de Sitter space. And so, but I think that there is a framework to resum those kinds of things in some circumstances, which I think is you know, extends, but includes stochastic methods. So what would be the calculation that you would like to see done if you have, if there's someone who thinks they have tools like that?
Yeah, so I think, yeah, I mean, also let me not paint myself as an expert on loops. I'm just trying to, I mean, to me, it's sort of an interesting thing that we should think about, but I have not studied it really in detail. But sort of the natural thing to ask would be, I guess actually there are many calculations that sort of disagree about what's going on. So some people think that if you compute, say, I don't know, one loop corrections to the power spectrum, that there are secular effects from time evolution in de Sitter space, which those are the types of things that I think you would want to resum and understand what's going on.
That's in like single field models or multiple field models?
I think just in single field models. But there are also other calculations, I think, some of them done by Guy, if he wants to comment, that actually, that diagram by diagram, there are secular effects, but they should actually cancel out of the fully resummed answer.
I thought in single field models that they were supposed to cancel out because it was a gauge effect, but that in multiple field models, it wasn't clear that they did.
Yeah. So exactly. There's some debate in the literature about whether it actually even happens in single field models. I think people have kind of converged on this secular effect does cancel out in single field models, but I think the literature is still maybe a little bit, I don't know, hard to penetrate. But sort of more generally, I think that, yeah, there are many partial results, but I personally don't understand the coherent story about loops in de Sitter. And so that's why I think it's an interesting thing to think about.
So maybe Austin, I can just comment on what you just said, because I thought also part of this debate about secular effects was, it was a bit apples and oranges, because, you know, there's a discontinuous difference between these effects in perfect de Sitter space and in, say, inflation, where you're kind of breaking the time translations and you're introducing a Goldstone or zeta mode. And then we know much more, we know non-perturbatively that zeta mode is conserved on large scales, but the zeta mode ceases to exist in de Sitter. And so it's hard to transfer actually those, you know, just by inducing a little epsilon, somehow you regulate these IR issues. At least this is how I somehow saw this. And a lot of these subtleties were just really arising in the limit, where you were studying fields on a fixed de Sitter background. And then, but the easiest way to regulate these things was just to kind of, you know, break that symmetry.
I know in one example that what happens when you go to a, say, a power law rolling, where you're kind of turning on a slow roll, you move where these infrared things happen. So they no longer happen specifically at zero mass, say, but they move around in the mass versus slow roll plane. But I didn't and I thought that for multiple field models, it wasn't that they were still there, even in the inflating case. Whereas for single field models, I think it's true. The gauge argument seems pretty convincing.
Yeah. Okay. Maybe from okay. I'm not sure what multiple fields.
Can I ask?
Sorry, can I make a comment about this? Sorry to interrupt. About Cliff's question, I guess. I think one thing that, well, I was educated on this by Sasha Polyakov, so I'm just echoing his intuition. But I think one thing that would be very nice to understand, or to show that the intuition is wrong, is to do a calculation in maybe perturbation theory on a background electric field, and see the avatars of the Schwinger mechanism showing that there's some instability, that the electric field wants to be screened and decay, some sort of correlation function, or I don't know what it is, and show that the precise analogous calculation in de Sitter space would not give you a large effect. Then I don't know what the calculation is, but maybe within this soft effective field theory, one can do something analogous for the photon, and in the Schwinger effect. But anyway, I think that this intuition of Schwinger effects and de Sitter space is pretty strong. And if you want to prove that de Sitter is stable, it would be nice to do a specific calculation with these two setups in mind, in which you show that there's something that's happening in the Schwinger case that is not happening in the de Sitter case.
So do you mean when you say Schwinger, I mean, normally we can reproduce Schwinger effect in QFT by thinking of Schwinger effect as annihilation of bunch of photons into E plus E minus. And then you can take the limit of photons in which you reproduce sort of a constant electric field. So there you can understand Schwinger effect as a limit of a very high occupation number of photons annihilating into pair. So you are suggesting to do the same in the gravitational background, or to treat gravitational background itself as a Schwinger story? So
no, to do similar calculation to the gravitational background. Yeah.
But what would be the information that you would get from there?
Well, no, but you're seeing in this calculation just described, you're seeing the Schwinger effect, but I think you would like to also show that the Schwinger effect is trying to destroy a background electric field. If you try to set it up,
that's right.
The pairs that are being produced are trying to destroy the configuration. And I don't know if you can set up and do a similar calculation in de Sitter. If you try to, I don't know, bundle up a bunch of gravitons in such a way that they will form a de Sitter geometry, that a back reaction from matter fields or self-interactions of the gravitational field will prevent these de Sitter states from being formed.
Well, actually, we see that explicitly in this coherent state picture of de Sitter. So in other words, exactly in the same way as you can think of electric field as a coherent state of photons in certain limit. In that case, of course, you are taking limit of zero frequencies. If you resolve de Sitter as a coherent state of gravitons, you see that what is the analog of Schwinger effect is not exact analog, but what is analog of Schwinger effect is Gibbons-Hawking radiation. So you literally see how the coherent state picture of de Sitter explains Gibbons-Hawking radiation as a Hamiltonian process in which gravitons rescatter and they produce more energetic quanta. So in that sense, yes, there is a one-to-one correspondence in some sense between Schwinger and de Sitter itself. But
the question, sorry, but the question is, can you reliably compute back reaction, for example?
But that's precisely the point. This automatically accounts for back reaction because you are resolving de Sitter itself as a coherent state. So it's like a process in which you have coherent state which depletes. So that's precisely the way we see that de Sitter quantum breaks, because in other words, that allows you to see that the Gibbons-Hawking radiation is not coming for free. Actually, de Sitter really decays in a quantum sense. So in a sense, de Sitter depletes and evaporates. And that's one way to see why de Sitter must have quantum breaking time. So it's not like avalanche time instability. It's not instability in the usual sense. It's a slow, very slow, gradual depletion, because of course still there are differences between electromagnetism and gravitational depletion. Because in Schwinger case, the main difference is that in Schwinger case, of course, charges can have two signs, and also electrons are much heavier than photons. Here, gravitons deplete into gravitons or into some massless stuff, and so that's the only difference, and that's what makes it the only. But otherwise, the conceptually, we see that the de Sitter ages because of this internal clock, which is. And by the way, this connects with I want to ask Daniel. You mentioned this data parameter, but you see in this picture there is an intrinsic quantum clock in de Sitter. And so the question was whether this zeta parameter, a version of quantum zeta parameter, would reappear in de Sitter. And yeah, I mean, there's this.
Sorry, I was just talking about the curvature perturbations, which become pure gauge in de Sitter. So they.
No, of course, it's no, that's different. But what I'm saying is that there is a quantum clock that de Sitter provides, And of course, this I call it zeta parameter in using a, maybe it's a wrong name, but there is a parameter that reappears because of this quantum clock. Okay.
I see.
I can see that Eva has raised her hand.
Yeah, hi. I'm not going to use my video because I'm on my exercise bike and no one wants to see that. Just be glad we're socially distanced. I want to make a comment related a bit to what I think everyone is saying, including Gia, which has to do with another interest of my own as well in this subject, which is the behavior of large endpoint correlators, which have a tree-level factorial growth. And in multi-field cosmology, that actually persists in a way that's easier to see than it is in Minkowski space. But in Minkowski space, there's been progress. And it seems to me almost kind of the reverse of what Gia is saying, in the sense that what people do there is they look at large charge sectors, and there's a lot of progress on expanding around large charge states or large charge sectors of theories. And for example, the way they make progress is precisely to find a semi-classical saddle point that governs the large charge amplitude. So this is the kind of thing that Ritazzi and collaborators did, and other people too, Komogodsky and I'm not, of course, Hellerman and company. And the thing that the disconnect with this discussion is that when you have such a large charge excitation, precisely what you want to do is a semi-classical description of that, not the other way around. So I just wanted to make that comment. I mean, it's kind of saying two things at once. One is that effect is important for our subject of cosmology and field theory and cosmology. And secondly, when it comes to these discussions of how you deal with excitations that are made of many constituents, I mean, semi-classics is the standard way to do that, and it's had some recent success as well.
Yeah, I mean, I don't know if anyone wants to answer, but yeah, I fully agree with this statement. So in other words, indeed, I mean, semi-classics works for high occupation number systems. Obviously, that works. Except what we are discovering is that when the system is saturated, and these are very special systems, when the occupation number is equal to inverse coupling, those systems, this semi-classical approximation gradually diminishes. So there are certain correlators which, after a certain time scale, this quantum breaking time, can no longer be accounted semi-classically. At least I could not find any way how to deal with them semi-classically. Maybe there is some way somehow to resum and.
Okay, I'm actually tempted to ask Gia the following question. What do you think of the Higgs explosion idea? This is in danger of derailing the discussion further, but I'm quite curious.
Yeah, so yeah, you mean to me. Okay. Was it to me, the question?
To you, yeah. I mean, I have my own opinion. But yes.
Okay, I mean, I don't know if the I would prefer to discuss when people that are supporting this idea are around, because they cannot respond. But I don't think a Higgs explosion in a weakly interacting standard model can work, because of the usual story. I mean, they are extremely well understood properties of high occupation number amplitudes, and in collision of two particles is extremely hard to produce high occupation number state, unless there is a specific condition met, unless the state that you are producing saturates the entropy bound. In standard model, if we literally take standard model as it is, there is no such candidate. Okay, the Higgs, the multi-Higgs states that the standard model can offer, they don't saturate entropy bound, and so therefore the amplitude of producing multi-Higgs states within the standard model, if you ask my opinion, I think that's exponentially suppressed. There is a danger there, because when people compute amplitudes, as you know very well, multi-particle amplitudes, they have this factorial growth because of number of Feynman diagrams increases. But that's a fictitious growth, because that growth cannot be trusted beyond when the number of legs in the diagram exceeds 1 over the coupling. Now, of course, if we naively extrapolate that, we'll get some miracles, but that's simply artifact of.
It's limited in kinematics, but the thing about cosmology is that we're led to that kinematics because the wavelengths expand outside the horizon, and so that's part of why one finds that actually in the de Sitter case, that effect persists much more than it does or it should in Minkowski space.
Yeah, in other words, right. So in other words, the story, so as I said, once we are dealing with systems that are saturons, I call them saturons, that saturate entropy bound, then the story is different. So if we're dealing with systems like black holes.
I'm just the original stuff of Voloshin and company was limited in kinematics. And I'm just saying that that's a huge limitation on applying it in normal Minkowski field theory, but it's a kinematics that's quite applicable in cosmology because of the way that we have this dramatic exponential redshifting of momenta. So it's a kind of nice irony where the de Sitter case is actually easier in this context.
Yeah, that could be. Yeah, in de Sitter, this is a little bit more subtle. In other words, so if I correctly understood your question, if we are dealing with let's say 2 Higgs going into many Higgses, amplitude with momentum transfer, certain momentum transfer Q, if we're doing that in the de Sitter space, and if momentum transfer becomes comparable to the de Sitter Hubble, then of course story has to be reconsidered.
Let me stop you. I'm not computing the Higgs thing in de Sitter. I'm just saying for cosmological correlators in de Sitter, we're in the easy momentum regime for this effect. That it's a slightly, I'm not applying the Higgs thing in de Sitter here, just to be clear.
All right.
That's why I interrupted you. So it's just although normally this limitation on kinematics is
I understand, yeah.
The reason why you can't extrapolate this n factorial in normal field theory here. It works. So.
Yeah. Okay. Yeah. Sure. I mean that's yeah. That has to be considered. So I cannot answer right away what happens in de Sitter with those type of amplitudes. But certainly, I mean, the de Sitter story is very different, especially when momentum transfer becomes comparable to Hubble.
Very nice. Well, I think we're coming close to the end of a long day for some of us and the beginning of a day for others. So I wanted to take this opportunity to thank again Gia, Austin, and Paolo for being our panel members, and to all of you who participate in the discussion for making it a lively and interesting discussion. Hopefully some of these papers that have been mentioned, maybe one of us will copy this chat into the Slack so that people have references, but please feel free to just ask on Slack for references and names. I think that one of the useful things of a workshop is that you get to explore parts of the literature that you were not familiar with. And otherwise, let me just mention tomorrow the workshop continues, but it switches gear into discussions of large-scale structures. And another reminder is that Friday evening, London time, there will be a public talk by a public event by first Eiichiro Komatsu and then Roger Penrose to celebrate Stephen Hawking's would have been 79th birthday. So if you're interested, you can follow that. And otherwise, I'll thank you all and see you tomorrow.
Bye. Bye. Thank you.